A common way of indicating what phase a substance is in at various temperatures and pressures is something called a phase diagram. So here is the phase diagram for, I believe, water. What you can see is the three phases are indicated, so solid, liquid, gas. If they're not labeled, the solid is always the one at the lowest temperatures and pressures. Gas is at the highest temperatures. And then as you either increase pressure or from the gas phase, you go over the vapor pressure curve and go from a gas into a liquid. So this curve here is called the vapor pressure curve, giving the pressure and temperature where that phase change happens. Then this curve is called the fusion curve, where melting and freezing happens as you move, as you increase in temperature at various pressures. Here is 1 atmosphere, so atmospheric pressure. So the normal melting point is going to be at 1 atmosphere and where you go from a solid to a liquid. The normal boiling point is over here where you go from a liquid to a gas at atmospheric pressure. Farther down here, you can see there are temperature and pressures where you go from a solid directly to a gas. So that's going to be low temperature and low pressure. You have the sublimation curve here. And let me just switch my color. Right here is the triple point. That is where all three phases, solid, liquid, and gas, are in equilibrium with each other. And so all three phases will exist together, and that only happens at that specific combination of temperature and pressure. One other thing to notice is that out here, the vapor pressure curve ends. You'll stop getting a solid line, and then often you'll see either a dashed line or no line at all. That's called the critical point. Above that temperature and pressure, you get a supercritical fluid, which is a phase that's kind of in between a liquid and a gas, has some properties of both, but it only occurs at high temperature and pressure. Here's what it looks like. So normally you have these two phases, gas and liquid. As you increase the temperature and you're at a fairly high pressure, eventually you get this supercritical fluid. You can see that the interface between the two phases disappears and you get the supercritical phase. So here's our phase diagram of water again. The normal melting point here at 1 atmosphere is 0 degrees Celsius. Normal boiling point is at 100 degrees Celsius. Our triple point for water is at 0.01 degrees Celsius and 0.006 atmospheres. And then the critical point is labeled up here. One other important thing to note, ice is less dense than water, which is why the slope of the line here is a negative slope. Norm for most other substances, you're actually going to get a positive sloped line there, indicating that the solid is more dense than the liquid. Here is a more complex phase diagram for water. The solid water ice can actually form different arrays in 3 dimensions, which is what all of these Roman numerals indicate. But again, you can see the critical point and the triple point there. Here's the phase diagram of carbon dioxide. Again, notice this line is a positive slope this time, which indicates that the solid is more dense than the liquid. For carbon dioxide, the 1 atmosphere line is down here. The triple point is at negative 56.7 degrees Celsius and 5.1 atmospheres. And solid carbon dioxide at room temperature, the liquid is not stable. And so if you get dry ice, it doesn't go through a liquid phase, it just sublimes at room temperature, going directly from the solid to the gas phase. So here's some practice questions for phase diagrams. Consider the phase diagram of carbon dioxide that's shown. What phase or phases are present under each of the following conditions? So 20 degrees Celsius and 72.9 atmospheres. So here's the line for 72.9 atmospheres. 20 degrees Celsius is going to be somewhere in here. So we're going to be at the liquid phase. Negative 56.7, 5.1 atmospheres. And I would, if I were you, I would pause this and make sure that you can do these before I tell you all the answers. So negative 56.7, and so we're here, and 5.1 atmospheres, we're at our triple point, so we're going to have solid, liquid, and gas present. 10 degrees Celsius, 1 atmosphere, 1 atmosphere is around, 10 degrees is going to be around in there, 1 atmosphere is here, so we're going to be in the gas phase. Negative 78.5 is marked here, and 1 atmosphere. We are going to be transitioning from the solid to the gas phase. And then 50 degrees Celsius, 80 atmospheres, so 50 is going to be up here, 80 atmospheres, we're going to be up at the supercritical fluid. So there's the answers. And I've mentioned as we've gone along that water is unique in its properties. This slide just spells out what's so important about it. It's a liquid at room temperature, whereas most similar molecular weight covalent compounds are gases. So ammonia, methane are gases, but because of hydrogen bonding, water's a liquid. Water is an excellent solvent. Most of the solvent discussion we do in this class is about water. That's because of its large dipole moment. And even some small nonpolar molecules can be soluble in water. So oxygen, carbon dioxide are both soluble in water. Water has a high specific heat capacity, which is what moderates coastal climates. That's why if you go out to Lake Michigan on a sunny summer day, the temperature drops as you get closer to the large body of water. It also expands when it freezes, which makes ice less dense than liquid water, which leads to the fact that ice floats on water, which allows for life in lakes and rivers and oceans.